About a paper. This paper, the name is Data-Driven Interarea Oscillation Analysis for a 100% IBR-penetrated power grid. I am the corresponding author, Lingling, and the paper has been published in IEEE OAJPE in January 2023. Okay, so let me just give 10 minutes, just 10 minutes to talk about the essence of this paper. This paper is about oscillation analysis, linear system analysis. And now let's talk about conventional method. What's the conventional method that we are using? And actually the paper is talking about IBR, a new challenge, inverter-based resources. And then we use an example of 9-bus system to show the new framework of analysis. Well, it's pretty interesting. So the conventional method of linear analysis is sort of like you have to build an analytical model. Now, analytical model is not a simulation model. They are different. For example, in PSCAD or SimScape, the physical system-based simulation model that give voltage current like sinusoidal waveforms, these are not analytical model. Analytical model means everything is phasor-based. You can initialize it. You can get the flat around. Then you can also do linear analysis by doing Jacobian linearization. So that means analytical. So now the conventional method is basically even if you have static frame models, you have to convert to the DQ frame for a generator. For example, Park transformation converts generator models to the DQ frame so that at nominal conditions, usually the state variables are constant. So therefore, you can obtain a linearized model in a batch. So usual way is just you build everything, do linearization, grab the linear model. The assumption is that you know everything. You know every component. What happens is that if you don't know anything, so this type of assumption is that you every component of generator, load, grid, everything you know. So then you can obtain the Interarea oscillation eigenvalue. You can plot everything like this type of thing. So now the new challenge is that IBR is actually a black box. You know, not inside information, you don't know anything too much about it. So what do? You still can get the input-output model, especially the voltage-current relationship using experiments. And then, based on the voltage-current relationship or impedance model, incorporate into the entire system. The entire system has to be an impedance or admittance model. So that's the method you are doing. For example, you can use frequency scan to have an inverter and scan it. So this is sort of like you have a controllable voltage source connected to inverter, so that you get the subsystems DQ frame admittance. And everything has to be DQ frame. Similarly, very similar to the Park transformation, that steady state is a sort of like constant value. So this is one example that we have done previously. Now, you have multiple machines and a grid, then what do you do? So in this case, just the source and load will not be enough. You have multiple models. In the power electronic, a lot of papers, this is limited. This method called admittance is limited to two components, the source and the load. And then people can check their loop gain and check its Nyquist. Or you can looking at the total admittance. Total admittance is Y source, Y load, and add together. So this method is expandable. In fact, you can calculate the eigenvalue using the roots, because this is expandable. You can build a bigger system to do that. You cannot do this one. This one you have to always form two subgroup, but this one is expandable. So therefore, we will move on to the next one to handle the large grid impedance, right? So the method is basically frequency scan. If you have every IBR's DQ admittance ready, you can fit it, and you have to obtain an S-domain transfer function matrix. Then you have the network admittance. Then you can combine together and carry out eigenvalue or mode shape analysis. So that is the essence of this paper or technology that has been this particular technology has been documented in another paper like 2020. So the idea is, for example, in the 4-machine system, we have the grid. which is a 4x4 matrix. And you can imagine this is just everything is transfer function based, or every component is actually small component is 2x2 in a DQ frame. Then you attach the generators YG1, YG2, YG3. So these are in the diagonal matrix, right? So you have to add them together. That is your big overall network matrix, but it is the S domain. What does it represent for? They represent, admittance represent the voltage multiply admittance, or admittance multiply voltage, that is current. In addition, you can do this. If the current injection, then the inverse of the admittance matrix or impedance matrix is the voltage. So this impedance matrix, in fact, is the closed loop system's transfer function, right? Closed loop system. So therefore, the zeros of the YS are the system eigenvalues, or the poles of the ZS, are the system's eigenvalues. So this is what we want to emphasize. So next, the measuring admittance, there are lots of techniques to do that. Basically, you have to set up the subsystem, right? You cannot directly use a big system to do that. You have to set up subsystems, component by component, measure that. Go to this 9-bus system. If you have 3 generators, the GFM, GFL, this inverter, you don't know the admittance, you have to measure that. So one by one, you measure 3 of them. So then you got 3 DQ admittance matrix. So this, every single one, it's measured, you have to fit in that. So that takes quite some time to make sure that you do vector fitting. You grab it, this time it's S domain model. Otherwise, it's just a frequent domain data, not model. After you got the model, now we put everything together. Now you have impedance model. Now let's talk about this one. So first you calculate the eigenvalues of the impedance, because you should be able to calculate just doing Y-bus matrix to do TF0. Then find out the Y-bus matrix is TF0 that you got. So for each eigenvalue, what will happen? It will make the Z matrix singular. All right. So if we decompose this Z matrix when it is plugged in, S is plugged in with lambda. Now what happens? This can be eigenvalue decomposed into left eigenvector, right eigenvector, and the row matrix. Maybe this is right eigenvector. Anyway, this is a vector, and we will particularly focus on first one, which is the infinitive one, that is ordered from the large to small. So this one is very large, almost infinitive. So the rest will be ignored, because this one is basically the dominant one at lambda I. And then you just look at this one, the cube, the column vector. So why do we want to? We want to do model shape analysis, because one of the, for example, one of the gamma eigenvalue will be, and this is the column that we should be looking at. The column vector can tell you a lot of information, saying, for example, which bus's voltage is more observable, because each column will be based on the system. Right? So for this example, we can grab a 9-bus system, or we can grab 3-bus system if we have done the node reduction. So let's take a look. The EMT simulation shows that the system has oscillations, and for example, bus 1 and bus 3, voltage oscillation against each other, and in frequency is same, in a real power, reactive power is same. So bus 2 is sort of like not oscillating too much. So that can clearly show that is the oscillation mode, about 3 Hz oscillation mode, that can be caused, or it is observable between bus generator 1, generator 3, on bus 1 and bus 3. So let's conduct a mode shape analysis, plugging in the eigenvalues in, and then check out the mode shape on the column. So we plot this column because each element of the column is basically a complex number. You can plot it. So that is clearly show bus 1 and bus 2. So bus 1 and bus 3, the blue and the black are against each other. So that shows this is the Interarea oscillation mode due to IBR1 and IBR3 interactions. Eigenvalue analysis is also presented here. It can be based on 9 nodes or 3 nodes because the network can be reduced. So it's found that this is basically, you can find the 3 Hz is at marginal condition. And this, a couple of them are not realistic. You can ignore that, but 3 Hz is there to show that this is 3 Hz oscillation. All right, so the next thing is about the matrix to validate this, to give more explanation. This is actually bus 1 and bus 3 relationship. So that can be based on subgroup analysis. For example, if we just look at IBR1, IBR3 and treat the other one just as voltage source, and then what happens is you can really doing some kind of eigenvalue analysis again, easily exclude the other set of IBRs and carry out eigenvalue and again and see what happens. So basically disable this and calculate eigenvalue again and show, okay, who was that? So this is additional analysis. So this additional analysis and it can show that even all 3 online versus IBR1, IBR3 online, that they have the same performance. But if you turn off IBR1, then actually they are very different. If you turn only a single one together, they are not the same. So that is clearly showing oscillation is because IBR1 and IBR3. So this is sort of like a one by one, just keep adding stuff and see what happens. Right? So additionally, Y-bus matrix decomposition is another very good method to show what happens. So for example, it is Y-bus matrix 3 by 3, but if we get rid of bus 2, then we have 2 by 2 matrix. And furthermore, you can keep decomposing it and make it a circuit like this. So in the end, you will find that exactly which circuit is having the model. So what we have found is that circuit 1 contributes 2 modes. One is poorly damped, blue line. Circuit 2 contributes 1 mode. Circuit 1, so this circuit, I think, is represent difference between 2 IBR. So in fact, this is I1 minus I3. The other one is I1 plus I3. So yeah, that all depends on how you do the system decomposition. So that's the entire thing about the Y-bus matrix decomposition to show what is happening. So by the way, ZM1 is a model impedance that is coming from this kind of combination. Right? ZM1 is related to the difference between the 2 generators. The other one, ZM2, the circuit is basically the voltage current is, look at that, this is a combination. So their difference causes this mode. So, and this is the blue one, IBR and lambda. So that's very clearly showing that, in fact, if we treat the IBRs as similar and check their difference, that is the Interarea oscillation mode. All right, so that's about it. So the concluding remarks is that power grid is having more and more IBRs, and their models and controls are proprietary information. In this case, how do you do work out eigenvalue, find out eigenvalue linear analysis, this type of thing? How do you detect or predict oscillation? That you can do as domain admittance-based eigenvalue analysis. So this one basically helps you to integrate data-driven method into stability analysis. And it is completely different framework because everything is voltage and current. So now you have to go to the mentality that treat everything as admittance and use the big admittance model to find out the eigenvalues. So on the other hand, this one continues to give us the mode shape information and can also help us to do subgroup analysis and through and network decomposition. Yeah, it's very helpful to help us to understand, find out the critical influence factor. Okay, thank you.